Hey there, Calc folks, back here with my first video in what is going to be a series of videos looking at some different integration techniques. I have several cases for different integration techniques we want to look at. We're going to take a look at the first one here in this video, that being integration by parts. But we're also going to look at trig integrals, trigonometric substitution, and the case of partial fractions, right? As we look at a couple of different, there are 4 different techniques for integration. Along with, we're going to develop integration tables. We're going to be mixing these ideas, and then we're going to even get into looking at calculating integrals with some different numerical integrations. And the case for improper integrals, all in this material, folks. So that is where we are heading with all of this. We are really adding to our techniques that we're already familiar with from calculus. Those are some fundamental techniques, along with U substitution. Right? You have some fundamental techniques along with a little U substitution, which gives us all of our integration techniques, folks. All right, up to this point. But we are going to look at a few more techniques and add them to our repertoire, in a sense. So, let me bring this up. This is integration by parts. All right, we are going to look at this topic of integration by parts. And integration by parts is an integration technique that follows from the case for product rule in integration. All right, by looking at the product rule and undoing that product or that differentiation in the product rule using integration, we can manipulate that result into an integration statement, right? That involves the product of 2 quantities. And this is known as an integration by parts problem. It is an integration technique that is often done when you might recognize that you have a product of 2 quantities inside your integrand. Excuse me. Product rule is a handy technique that sometimes does apply. Now, or integration rule is a handy technique that does apply. And it does follow from product rule for differentiation, folks. Right? And recall, product rule from differentiation says that if you have these 2 functions of x, u of x and v of x, we understand from product rule, if we take the derivative with respect to x on both sides, this is equal to the following result. It is equal to u prime of x, the first derivative of u, times v of x, added to u of x times the first derivative of v. All right, this is the product rule for derivatives. All right, now we can undo this product rule, right? Or in a sense, we can undo this differentiation in the product rule seen here on the left-hand side if we apply the integral operator with respect to x on both sides. And that is what we are going to do to develop this rule. What we see initially here is the development of the rule. And we apply the integral operator with respect to x on both sides of the above relationship. We apply it to the left-hand side as we see here, and we apply it to the right-hand side as we see here. Now, when the integral operator is applied to a derivative with respect to x, and where you're integrating with respect to x, all of that integration undoes the differentiation. Those are inverse operators, and there's some canceling of the operation that occurs on the left-hand side. Over on the right-hand side, right, that integral operator will apply itself to this summation, the sum of these 2 terms seen on the right-hand side. And it will distribute itself across these 2 terms. You'll have the integral of u prime of x vx dx added to the integral of u of x v prime of x dx. All right. Applying the integral operator to the result given by the product rule produces this result seen here. All right. Where, furthermore, we can take note, since du dx is equal to u prime of x and dv dx is equal to v prime of x, right? Letting u equal u of x and v equal to v of x, when you consider their first derivatives with respect to x, du dx would be u prime of x and dv dx would be v prime of x. Implying if we multiply both sides by dx, right, in each case, you'd be able to say that in this first case that du would be equal to u prime of x dx and dv must be equal to v prime of x dx. Where you will notice I will go up into these two above integrals, and in the case of u prime of x dx, replace that with du. And in the case of v prime of x dx, replace that with dv in quantity. So the integral statement I see above, this statement above, u of x times v of x must be equal to the integral of v of x du plus the integral of u of x dv. Where we understand both that du is u prime of x dx and dv is equal to v prime of x dx in value. Now what we are again doing here, folks, is just going through where the development of the integration by parts technique comes from. All right. If we now solve on the left for this value seen here on the right hand side, the integral of u of x dv, we develop the rules seen in the integration by parts. Where what we say in integration by parts is that the integral of u of x dv is equal to u of x times v of x minus the integral of v of x du. Right? That technique is known as integration by parts. We can approach an integral as we see it here on the left-hand side, if we can approach an integral as we see it over here on the left-hand side. All right? And identify from that integral what would be u of x in value, and identify from that what would be dv in value. We can use our calculus to find du and v respectively, where with u and du and v respectively, we can then calculate u of x times v of x minus the integral of v of x du. Right. And folks, I can go all day repeating that back and forth, but it's not until we actually see an example that it might feel begin to feel like a process, right, that is doable. Right? This does feel a little like it can be a little confusing, let me say it that way, at least to begin with. Let me get to some example here, hopefully to help clarify. Now all of this is presented in an integral form, where if we let u equal u of x and v equal v of x, what we often say is that the integral of u dv is equal to u times v minus the integral of v du. Right? Replacing the u of x and the v of x in the above result with just u and v respectively. Furthermore, we're going to be doing these calculations in the definite context, where then that would be the integral from a to b for u dv is going to be just u times v evaluated from a to b minus the integral from a to b for v du. And we see this result for the case of a definite integral calculation. All right. Now I'll do examples of each here. Before we do, I do give you a little bit more to go on. All right, I see a quick little correction I made here. I just brought this and gathered this all together as a statement there, so you'll notice that. Let me just go ahead and scroll over here and center up also. Excuse me. But in the formulation of integration by parts, for that statement we see on the left-hand side given by the integral of u of x dv, that does stand for the integral of u of x times v prime of x dx. It does stand for this integration that we see here on the right-hand side, where it might be this integration here on the right-hand side that we use as an understanding of our setup for integration by parts. All right. To begin with, in this setup, you are going to have to identify what u is. Right? You're going to look for the integrand and try to identify from the integrand what you might call u. That will be some function of x. We might refer to it as u of x. And that will imply that the remaining portion, v prime of x dx, would be equivalent to dv. Where, from differentiation applied to u equal to u of x, you would be able to find u prime of x, and thus be able to develop a definition for du seen in our result for integration by parts, du equaling u prime of x dx. And from integration, right, be able to integrate the quantity dv, right, be able to integrate this quantity dv, which would be like integrating v prime of x dx, to obtain what we would understand as just v of x. Right? With du and v of x identified, along with our understanding of just u itself, we could use u times v minus the integral of v du and form our result using integration by parts. Where I see this is lacking a little bit, we might say here. Yielding, let's say it this way, yielding du and v of x. Right. What we might say are the remaining parts seen in the result for the integration by parts. Right? I do think I want to say that there. Right? This is what's going to yield du and what's going to yield v of x. Excuse me. Used back here in our integration by parts result. The result seen here on the right-hand side. You are going to need v of x, and you are going to need the quantity du in that calculation. Right? Du will come from integration or differentiation. V of x will come from some integration. Now let's look at an example, right, to help us understand this. Here we have the integral of the quantity x sine x dx. Right? Where, when looking at this in the mindset of integration by parts, you're going to want to look at this as the integral of u dv. Right? The way you're going to want to look at this statement here is you are going to want to look at it in a sense as the integral of what would be some function u of x times some function which would represent v prime of x, all with respect to x, where v prime of x dx is going to become the part of integration by parts known as the value dv. Now you might be able to spot what is our u of x and what is our v prime of x dx in this example. All right? U of x might be the value x, where dv would be the value sine of x dx. If we consider letting u equal x, that does imply through differentiation that du dx would be equal to 1, or du would simply equal dx. And letting dv equal sine x dx, from integration we can find v. V is going to be the integral of dv, which would be the integral of the sine x dx, which would equal negative cosine of x. Right? V equal to v of x would equal the integral of dv, or the integral of sine x dx, which is negative cosine x, seen here. Right? And that, folks, gives us the remaining two parts, du and the value v of x, negative cosine of x, right? Where we can use these parts in our integration by parts result. Right? So following from integration by parts, the integral of sine x dx, which equals the integral of u dv, would be equal to u times v minus the integral of v du, where u we have identified to be x, v we have calculated to be negative cosine x, and we're going to subtract from that the integral of v du, which is going to be the integral of v, which we've identified to be negative cosine x, all integrated with respect to du. Du we've identified to be dx in value. We simplify this result now. This is x times negative cosine x. That is negative x cosine x. And here we're going to have the opposite of negative cosine x's antiderivative, which is really just the sum of the cosine of x's antiderivative, which we understand is just sine x. Right? Which we understand is just sine x. So our result given by integration by parts is just negative cosine x plus sine x plus c in value, folks. That is our integration by parts. Thus, from integration by parts, the integral of x sine x dx is the opposite of x cosine x plus the sine x plus c in value. Right? Again, the integration by parts begins by identifying what is the value of u, where you can use differentiation to figure out what might be our statement of du that I need down here in my result right here. U also being used right here. Once you identify u, you can then go back into your integration here and figure out what's going to represent dv, this value v prime of x dx. Well, if u is x, everything else, sine x dx is going to be dv. Or, yeah, dv. Where with dv equal to sine x dx, we could use integration on dv to figure out what would be v. The integral of dv, which is v of x, is the integral of sine x, which is negative cosine x. With those three parts, u, v, and du in value, we can produce this result seen in integration by parts. Take note. All right, folks, that's just our first example. Let's scroll down and see another case here. There is also the case for the definite integration by parts. So I say let's consider next the integral from 0 to 1, right, for x times e to the 2x dx. And again, how we want to begin looking at this as an integral of u dv, right? Or what we might think of as more formally u of x times v prime of x. Let's do v prime of x dx in value. Where what's going to work for us is if we let u equal x and let v prime of x dx dv be the quantity e to the 2x dx in value. All right. If we let u equal x, again du will just simply equal dx because du dx will be equal to 1. And letting dv equal e to the 2x dx implies that v, which is equal to v of x, right, which would be equal to the integral of dv, would just be equal to the integral of e to the 2x dx, which is 1/2 e to the 2x in value, following our integration rules. All right? E to the kx is 1/k e to the kx in value. And those are our three parts, folks. We need to know u, and u is equal to x. We need to know v, or v of x, which is 1/2 e to the 2x. And we need to know du in terms of x. And that is simply dx. With those three values, we can form our result for integration by parts. So for integration by parts, using the definite integral, it is just going to be u times v integrated from 0 to 1 for the integral minus the integral of 0 to 1 for v du. That represents the integral from 0 to 1 for u dv, where we know u is x, v is 1/2 e to the 2x, which we're going to evaluate from 0 to 1. At 0, it does 0 away, but at 1, it becomes 1/2 e squared. This result seen here. Minus the integral from 0 to 1 for v du. Well, v again is 1/2 e to the 2x, so that would be minus 1/2 as a constant multiple out in front, the integral from 0 to 1 for e to the 2x dx. Which we know the integral, the antiderivative of e to the 2x is 1/2 e to the 2x. So our constant multiple out in front would become negative 1/4 with the other 1/2, the inclusion of the next 1/2 in the antiderivative, for e to the 2x evaluated from 0 to 1, which at 1 is e squared and at 0 is 1. So it's e squared minus 1 in value for that antiderivative evaluated across those bounds. So in the end, we get 1/2 minus 1/4 e squared minus 1, or that can be simplified a little further. Distribute the negative 1/4, you obtain this result, which simplifies to 3/4 minus 1/4 e squared in value. The result seen here at the end. Might as well. Bring that result down here, just so it's a little easier to see there in the end. All right. Again, integration by parts using definite integrals here, folks. You just evaluate u and v across your bounds when you find the values of u and v. And your remaining integral, the minus integral of v du, gets evaluated also across those bounds from 0 to 1. Right. In this case, u is equal to x again, which implies du dx was 1, or du is equal to dx. And letting dv equal e to the 2x dx, we can use integration to find v, which was 1/2 e to the 2x. And all of that set up into the rule known as integration by parts. All right. I got one more example for you. We end up with this result here. That's thus this. But one more result here quickly in the notes I want to present, because I don't want to go too long with these, and I will certainly present more examples in class. We'll take this a little further in class, most certainly. But the integration by parts can be used to develop a calculation for the integral for the ln of x dx. We have yet to learn an integration rule for the integral of the ln of x dx to develop a, what we might say is an antiderivative rule for f of x equal to the ln of x, right, which would be the integral, the antiderivative of the ln of x dx. And the way this is done, in this case, we let u equal the ln of x. That does imply du dx is equal to 1 over x, or when we think about the quantity du, that is simply 1 over x dx. This will end up implying that dv is simply dx in value. which implies through integration that v must be equal to x. So from integration by parts, the integral of the ln of x dx, which we might think of as the integral of u dv, which is equal to u times v minus the integral of v du, is equal to x ln of x for the quantity of u times v, minus the integral of v du, which simplifies to just the integral of 1 dx. And the integral of 1 is just x. So here we end up with x ln of x minus the integral of 1 dx, or x ln of x minus x plus c. And this is the integration result, the antiderivative rule for the ln of x. The antiderivative of the ln of x is x ln of x minus x. Right? That is its description of behavior. And we develop that rule using a little integration by parts. All right? So that is integration by parts, folks. It is the the first technique we learned coming back to Calc 2 after learning some of those fundamental techniques and use substitution back in Calc 1. We returned to Calc 2 looking at a lot of application of integration, but we want to now focus in on some more integration techniques, and this was our first technique, this technique known as integration by parts. It does follow from product rule, right, where letting u and v represent some function of x in our calculation here. The antiderivative of u dv, right, the integral of u dv, could be then thought of as u times v minus the integral of v du. Right? The result given here in integration by parts. Similarly, there is an there is a definite integral calculation using integration by parts, and it applies itself rather intuitively to the result seen for the antiderivative calculation using integration by parts. All right. And it is a game of identifying your part u and dv, and using differentiation with u to find du, and using integration with dv to find this part we define as v, and using our result here and here. All right. Folks, I will be back for more examples in class over these techniques, but this does get some of the fundamentals out of the way. We can make the game a little harder if we want. Not that we want to, right? But the game does get a little harder with integration by parts, and we're going to see some of that develop in class. All right. So this is the fundamentals, though, for the technique. Take note, and we'll be back in class to go just a little more in depth with this calculation. And I will see you folks all then.